Hello, 160 students. This is Christina Howard, your instructor, and this is the screencast for the Chapter 2, Part A PowerPoint, where we talk about atoms, subatomic particles, and rules for chemical bonding. In the next PowerPoint, after this one, we'll cover things like molecules and intermolecular forces, etc. So, let's get started. The first thing we have to address is what matter is. So matter is anything that occupies space and has mass. So basically everything you've interacted with for your entire life is made of matter. And matter is composed of elements. So elements are familiar substances to you. They all have names. They're things like iron, nickel, carbon, helium, etc. So these are substances that can't be broken down or transformed into anything else by chemical means. So I can't, for example, take an atom of hydrogen and break it down into two smaller hydrogens. It's not going to work. It's as small as it can possibly be. So far, 118 elements have been identified. 92 types occur naturally, meaning that nobody created them. We just found them. The other kinds that are not created naturally are ones that have been synthesized in a lab. So basically, theoretical chemists imagine an atom that could exist and then try to get it to exist. And some of them do, they're just not very stable. 30 types are found in living cells. So that's obviously a lot less than the 118 we have to start with. So that simplifies our task as biologists somewhat because we only have 30 or so elements to worry about. And of those 30, fewer than 20 are the most important kind. So elements exist at room temperature as either a solid, gas, or liquid. And you can make them change phase by changing their environmental conditions, primarily temperature or pressure. Every single element is made up of atoms, and atoms are the smallest component of any element. So, like I said, I can't take a hydrogen atom and break it up into two smaller hydrogen atoms. That isn't possible. So those are the smallest possible thing to be. So here we have a model drawing of an atom. And this is just a way to represent the locations of various subatomic particles relative to each other. So a real atom doesn't quite look like this, but it's an easy way to illustrate the concept in a way that's close enough close enough to reality to be easily teachable. So at the center of an atom, we have a clump of particles called the nucleus. So in the nucleus, you typically find protons and neutrons. You'll never find electrons, which are these guys, in the nucleus. Electrons have different rules. So protons have a mass of 1 and a charge of 1. Neutrons have a mass of 1 and no charge at all. So neutrons are not electrically charged particles, but they do carry mass. Electrons are negatively charged, as you can see, and these whirl around the center of the atom. They whirl around the nucleus, sort of like satellites orbiting the Earth, but not in any fixed trajectory. So they could go this way, or they could switch directions and rotate around this way. So their rotation axis isn't planar. They don't rotate in one plane. They can rotate in any number of planes. And these guys do actually have mass, but it's so vanishingly tiny that we functionally consider the mass to be 0. So functionally 0. Okay, did I skip ahead? I accidentally clicked slide advance. No, I think that's everything I wanted to say in this slide. Okay, so moving on, properties of atoms. For every element, there is a specific atomic number and a corresponding atomic mass. So the atomic number is the number of protons in the nucleus. So here you can see the 2 protons. If I count these, 1, 2, the atomic number for this is 2. The atomic mass is protons plus neutrons. So protons determine the behavior and the identity of the element, and neutrons contribute to the mass. So this particular atom has an atomic number of 2 and a mass of 4. So 2 plus 2 equals 4. So this actually happens to be helium. So if we look at helium, that's the symbol for helium. In the periodic table, we would see, I don't understand why it does that, but it does. We would see the helium symbol in a little rectangle, and then somewhere, typically right below, but not always, is the atomic number. And then there will be another number that is a little bit more than 2 plus 2. And we'll get to why there's this additional post-decimal point number in a little bit. So usually the real actual atomic mass of an atom is a little bit greater than just adding up the numbers of protons and neutrons. Okay, so isotopes. Isotopes have the same number of protons in the nucleus, but they have different numbers of, and that's one of the errors that I caught, not electrons, but neutrons. So if you're using this outdated PowerPoint that has yet to be corrected, I think I updated it on Canvas. Just make sure that you cross out electrons there and put neutrons. Okay, so here we have 3 species of carbon. Carbon 12 is the carbon that weighs 12 atomic mass units. So here we have 1, 2, 3, 4, 5, 6 protons, and 1, 2, 3, 4, 5, 6 neutrons. And that makes up the majority of the carbon on Earth. So let's draw ourselves a periodic table rectangle here. We're going to put C for carbon. We're going to put 6 for the atomic number, and we're going to put 12 point something 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 for its mass. Carbon 13, if we go ahead and count the neutrons here, we can see 1, 2, 3, 4, 5, 6, 7. So this particular isotope has 1 more neutron than it does protons, meaning that it weighs 1 atomic mass unit more than carbon 12, so 13. Carbon 13 only makes up about 1.1% of Earth's total carbon. So compared with carbon 12, it's rare. Even more rare is carbon 14. So carbon 14 has 8 neutrons and 6 protons, and this makes up less than 0.1% of the carbon on Earth. And because carbon 14 is rare and it is unstable, meaning that it tends to decay because the neutrons don't necessarily like to stay in the nucleus, we can use it for something called carbon dating. So isotopes are very, very useful in dating objects that are no longer alive. So we can stage objects by developmental trajectory and such. So if you want to know how old like a horse is, for example, you might look at its mouth and look at its tooth wear patterns. But once organisms have passed, there's not a good way to tell when they passed. Until now. So, or rather, I'm using the word now loosely, until this technique was developed theoretically in the 1940s by Willard Libby. So Libby observed that if an unstable isotope is in a sample, it's going to decay, like I said. So isotopes that have lots and lots and lots of neutrons packed into the nucleus tend to shed radiation of some kind and decay into a different form. So when living material is formed, it has a precise ratio of C12 to C14. So another way to write this is C12 colon C14, or you can write it as a fraction. And this is based on the constant rate of cosmic ray bombardment. So part of the reason that alternate isotopes of various elemental species exist is because of cosmic ray bombardment. And that's exactly what it sounds like. So they are rays of radiation of various kinds from the cosmos that bombard and pass through the Earth, altering Earth's chemistry. When living material dies, it stops exchanging carbon with the natural environment. So, and I'm emphasizing the word exchanging here because definitely during decay, carbon from the decaying organism is given up to the environment, but it's no longer an exchange because the organism isn't accepting any carbon from the environment. So once that happens, the C14 that is still in the sample, in the deceased organism, begins to decay, because it's unstable, at a precise rate, and this rate is known, it's quantifiable. So the known rate of C14 decay is, the half-life is 5,730 years. Now, half-life is a term that you may not be familiar with. So what half-life means is time it takes for half the C14 in the sample to turn into N14. Oops. So that's the half-life. It's the time it takes for half the C14 to be transmogrified into something else. And we know that that takes 5,730 years. So if we know the starting amount and we know how much is left when we collect it, we can do the math and figure out how old the thing is. So measuring the ratio of C14 to C12 can tell us how long ago the organism died, and that's really useful for paleontology and also for things like verifying the identity or validity of supposed antique objects, because, you know, people do make money by faking antiques. Great way to tell if it's really an antique is to carbon date it. Okay, so I've been drawing you little periodic table rectangles so far, and here's another one. So exactly how the periodic table boxes are set up is a little bit dealer's choice. So if you go Google periodic table in Google image search, you're going to see a lot of different versions of this same thing. The thing that doesn't change is the arrangement of the boxes within the table. So those have a fixed position because the elements are arranged according to specific properties. So they're arranged into columns and rows based on the characteristics of the element. So here's an example. Is it a metal? Okay, what kind of metal? So we have alkali metals, transition metals, alkaline earth metals, and other metals. We have nonmetals, and then we have gases, lanthanides, actinides, and things with unknown chemical properties, so stuff that we're just not sure what it does. So the shading, the colors, and the columns point to shared characteristics. So for example, these sort of peachy beige guys are the transition metals. The rows correspond to the number of electron shells present. So if you go over to this side, you can see that there's numbers here. So hydrogen and helium only have one electron shell. Lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, and neon all have two. Sodium, magnesium, aluminum, silicon, phosphorus, sulfur, chlorine, and argon have three, and so forth. And if you look inside of the box, you can see, indeed, as promised, here's an atomic number, here's a relative mass that's a little bit more than the atomic number, and there's the name. So lots of information packed into one little box. Oh, I just remembered something. So let's go back to the isotope slide for a moment. Okay, so I mentioned that usually the mass, as calculated and stated in the periodic table's rectangle, is actually a little bit more than the addition or sum of the protons and neutrons. So for carbon, it would be 12 point something something something. The reason for that is that 12 isn't the only kind of carbon that exists on the Earth. So if you want to have a true average mass for all of the carbon, you need to include proportionally this kind and this kind. So because these, which are a little bit heavier, are included in the average, you get 12 point yada yada yada. And it's a small number because the relative abundance of these is small, but it's still significant, so it's included in that mass. I hope that makes sense to everybody. So if you look here, as you can see, it says 12.11. Okay, moving right along. I just showed you how the table is arranged according to number of electron shells, so let's talk about what a shell is. A shell is the sort of spherical shaped area in which a particular electron is able to rotate around the nucleus. So they are at a fixed distance from the nucleus, and they have a particular energy level and a particular number of electrons they have to have. So I'm going to write the definition here. Okay, so the first shell, and we number them from in to out, so this is 1, this is 2, and this is 3. So the first shell holds a maximum of 2 electrons. The second shell holds a maximum of 8, and the third shell also holds a maximum of 8. So because the atoms that we deal with in biology are limited to only about 30 elements or so, almost all of the atoms that we think about when we think about biological chemistry obey these rules. They want either 8 or 2 electrons in their outermost shell. So filling and emptying electrons into and out of an atom happens in the same way that pouring out or filling a glass of water works. So when electrons are loaded onto the atom, the first shell fills up first, the second shell fills up second, and the third shell fills up third. If the atom needs to give away electrons, it's going to first choose electrons from the outermost shell, and if those are all gone, it will choose electrons from the next shell. So it's sort of like you can pour out a glass of water, but you have to pour out the top liquid first. You can't choose to pour the bottom liquid out first. And same deal, you can't really fill a glass of water from the top down. You must fill it from the bottom up because that's how gravity works. Same principle applies to filling and emptying electron shells. So, atoms will fill the lowest energy shells first, and those are the ones that are nearest to the nucleus. They fill higher energy shells later. So hydrogen has 1 electron. That's pretty easy. We know that the innermost shell can hold 2, but hydrogen only has 1 and it has no neutron. Here we have helium again. So helium has 2 protons, 2 neutrons, and 2 electrons. Lithium has 3. So the innermost shell is satisfied, it has 2. The outer shell would like to have 8 electrons in it, but only has 1. Beryllium has 2 and 2. So beryllium would like to have 6 more electrons in this outer shell to meet its shell fulfillment needs. Here's boron. Here's carbon. So if we count, carbon has 1, 2, innermost shell filled, 3, 4, 5, 6. So there are 4 missing electrons from its outer shell. And it's for this reason that carbon likes to form 4 bonds. We'll go more into that later when we get to covalent bonding. So let's moving right along. Nitrogen has 7. Oxygen has 8. Fluorine has 9. Neon has 10. And sodium, with a 3rd electron shell, has 11. So let's look at sodium for a moment. If I tell you that atoms want to have their outermost electron shells filled, and I'm putting want in quotes here because, of course, it's an atom. It doesn't have a brain or preferences. This is just describing the behavior of atoms. So atoms want to have their outer electron shell full. Sodium can accomplish this two ways. Either it can laboriously collect more electrons to add to its outer shell, or the easier way is it could just get rid of this one. Because sodium is very, very, very desperate to get rid of this electron to meet its octet, so octet refers to the fact that there are 8 electrons here, that makes sodium extremely reactive because it's so, so, so close to getting its octet met, but it's not quite there. So here is what I just said, restated. So atoms want to fill their outermost shells first, and that's because this is the atom's lowest energy state. So to do this, they either donate or accept electrons from other elements. So I mentioned that sodium really wants to get rid of that spare electron, so it would be likely to donate it to someone else. So we call the outermost shell the valence shell, because that's the shell that it uses to interact with the other elements in the world. And an electron in that shell is called a valence electron. So the trading or giving away or accepting of electrons is the basis for chemical bonding. So when atoms interact with each other, they tend not to trade or give away or take neutrons or protons from each other. They do chemical bonding by exchanging electrons. So I already stated this, but it bears repeating. So it's called the octet rule. So oct means 8. And that's because for shells 2 and 3, those shells want to have 8 electrons. The innermost shell wants to have 2. So today we're going to look at 3 kinds of chemical bonds. The first one is ionic bonding. So this tends to form crystals. Covalent bonding tends to form molecules. And hydrogen bonding is a special case that we'll go into more later. Okay, so I mentioned earlier that sodium, and here's sodium, its abbreviation is Na. So sodium desperately wants to get rid of this pesky electron, and that's why it's so reactive. So I showed you guys in lecture that video of sodium exploding in Lake Lenoir in Washington. So you can see a real-world example of what that looks like. So what happens when sodium is aggressively getting rid of its electrons. Chlorine has the opposite problem. So if we count the electrons in this shell here, there's 1, 2, 3, 4, 5, 6, 7. So there's this missing spot. This is perfect, though, because sodium has what chlorine wants. Now I want to stress, sodium is dangerous, obviously, because it explodes. Chlorine is dangerous. It's a gas in its room temperature form, and it's extremely poisonous because it will go around and rip electrons off of things. Fortunately, if you get these two next to each other, what ends up happening is sodium is going to donate its pesky extra electron to chlorine, which is going to gladly accept it. The result is that now they both have 8 valence electrons, and they are happy, so this renders each of them less reactive than their normal form. Now we have to think about the relative amounts of protons and electrons. So in neutral species, which are these two, the number of protons equals the number of electrons. And when that is true, the pluses cancel out the minuses, and so the atom has no net charge. Even though it may have charged particles, they sum up to 0. So when we consider the charge of an atom that has gained or lost an electron, we have to count the relative numbers of protons and electrons to determine whether the atom has a net positive or negative charge. So sodium here has lost an electron, so it's given away a unit of negative charge. Now, although its valence electron needs are met, it's lost a unit of negative charge, and now there is now one more proton. Oops. One more proton than electron. So sodium gets a net positive charge. Chlorine, on the other hand, has now received an extra electron beyond its normal needs, and so now it has one more electron than proton. So it's going to get a negative charge. Oops. So these, I want to stress, are full charges. So what I mean by full charges is it's not a partial charge, it's not the result of sharing an electron, it's an electron has been given away or taken from, resulting in a full positive or full negative charge. So because opposites attract, once this electron transfer has occurred, now we have two charged particles, and they like to hang out next to each other. So this is an example of one sodium and one chloride, but if you do this to lots and lots of sodium chloride atoms, they tend to like to hang out next to each other in a crystal structure. So the reason that ionic substances are usually crystals is because they like to form arrays like this. So if I were to draw a salt crystal, it's going to have, and let me get some colors here. Let's go with purple for sodium, just to make sure that we're staying in keeping with the drawing. So let's say I have an array of sodiums that looks like that. They're going to sort of orient themselves so that they're all near a chloride. And as you can see, this shape has sort of a box-like shape. So anytime atoms arrange themselves such that there is repeating geometric patterns in their arrangement, that's called a crystal, and that's the kind of shape that ionic bonds tend to create. Okay, so that story was a story about one atom gifting an electron to another. But that's not the only way that bonding happens. So sometimes it's more favorable for two atoms to share a pair of electrons. So that's what's happening with covalent bonds. So if we looked at this word and break it down, co means together, and valent refers to the valence electrons in valence shells. So covalence is the sharing of electrons across two valence shells. So in covalent bonds, atoms will share electrons to fill their valence shells. So here's, for example, how water is formed. We've got two hydrogens and one oxygen. Now notice, each hydrogen would like to have another electron in its outer valence shell, because the innermost valence shell has 2 and a maximum of 2. Oxygen, let's count our electrons here, 1, 2, 3, 4, 5, 6. So oxygen's missing 2, and you might be wondering, well, why don't these two just pair up? They're not correct for each other. So not only do atoms like to have 8 electrons in their outer shell, but those electrons typically come in pairs, and they don't like to be singletons, and they won't pair up with just anyone. So the basis for electron pairing is that within a pair, one electron spins up and the other one spins down. And that's a nuance of chemistry that we won't get into much more. I just wanted to explain why they like to be pairs. So if you get hydrogen and oxygen near each other under the correct environmental conditions, typically with some heat to catalyze the reaction, what you end up getting is oxygen and hydrogen collectively agreeing to share a pair of electrons. Now, if we count, each hydrogen has valence electron count of 2. And the oxygen, if we count, has 1, 2, 3, 4, 5, 6, 7, 8. So valence electrons for oxygen equals 8. Everybody's valence needs are met. Everyone is happy. So that is a covalent bond. And in covalent bonding, because these electrons are shared, covalent bonds are harder to break than ionic bonds. These are stronger. Sorry, I keep doing that. My hand keeps touching the wrong place on the screen. There we go. Okay. You might also notice that this particular molecular arrangement, so a compound held together with covalent bonds, we call a molecule. So this is a molecule of water. And notice that instead of having the arrangement, there's an angle. In this case, it's 90 degrees. So there's a reason for that angle. The reason for that angle is that these electrons in these pairs are not shared equally. So why wouldn't they be shared equally? Why aren't all atoms sharing equally with their friends? Well, different atoms have different electronegativity. So what this word means is the ability to attract and hold on to electrons. So in the periodic table, electronegativity decreases as you go down, and it increases from left to right. So if you were to make a heat map, you would see various hot areas where there's high electronegativity and various cold areas where there is very low electronegativity. So the differences in electronegativity between atoms influences the properties of the resulting molecules. Specifically, and what matters most to us is it polar or not? Polar means has a plus end and a minus end. So if the sharing is equal across all spatial planes, then the resulting molecule is not polar. If the sharing is unequal, it will be polar. So here are two examples. Here we have water. Again, note there's a bond angle. And also note that we have these little symbols here. So that's a lowercase delta. And what this means is this charge is partial. So a full plus, like you have in Na+, this plus represents an absent electron. So it's a full unit of positive charge. A lowercase delta plus represents a partial positive charge. So that's what this means. And they can be partially positive or partially negative. So I'm going to explain the basis for this briefly in this PowerPoint because I want to get to the end of it, but I'm also going to make a Khan Academy style video that will get more into the basis behind partial charges. So stay tuned for that after this. Maybe after Tiki goes to bed because she is running around right now and distracting me mightily. Okay, so the water molecule depicts a polar bond, which is a charge across the molecule. So as I promised, there is a plus end. In fact, there are two, and there is a minus end over towards the oxygen. So this end of the water molecule, the one that's facing the words, has a slight positive charge, and the oxygen end has a slight negative charge. If all of the bonds are equal in sharing, or equal across spatial arrangement, so equal in sharing is represented here. This is O2. And over here, we have methane, so CH4. Note there is radial symmetry across this entire molecule, so there is no direction in which it is not symmetrical, and that means that it is also nonpolar. So there's no partial plus or partial minus end. So, using electronegativity to determine bond type, you can look up electronegativity for any element. And you can do it very easily using the internet. So, basically what you want to do is look up the electronegativity and then perform some subtraction and see what the difference is. So if the difference is more than 2, the result is an ionic bond, because an electronegativity difference greater than this is just going to cause electron transfer. If it's between 0.5 and 2, the result is going to be a polar covalent bond. So this means unequal sharing. And if it's less than 0.5, the result is a nonpolar covalent bond. So here's nonpolar covalent, and note this blue haze here that's adopting particular shapes. This represent electron clouds. So remember I said that the electrons like to orbit the nucleus of an atom, not in one plane. So if you're having a hard time imagining that, planar orbit is what the rings of Saturn look like. So instead of having particles careening every which way around at a fixed distance from the object, they are within one flat plane. That's planar orbit. So electrons don't obey this principle. They rotate however they want to at a fixed distance, which creates a cloud of probability where you would be likely to find the electron because it's in motion and it's very fast. So when the haze is distributed evenly, but spans the space between the two nuclei, that's nonpolar covalent. When the haze is unequally distributed between the two nuclei of the joined atoms, that's polar covalent. So here we can see partial negative and partial positive, and partial negative is because this haze is a haze of negatively charged particles. And easily observed here, if one electron has been given to one atom, as it has been here, then the hazes are completely separate because there's been a transfer. Okay, so if we know that it's possible to form partially charged molecules, they're not fully charged, they're partially charged, it would make sense that when you get them together in a container, they're going to orient themselves relative to each other such that the plus ends and the minus ends are near each other, because we know opposites attract. Even if they're not full opposites, they are still attracted to each other. So this is what we call hydrogen bonding. And hydrogen bonds are weak bonds, so individually they're not very strong. They're less strong than an ionic bond or a covalent bond. So individually they are weak, but collectively they are very, very strong. So the proper definition is the bond that forms between slightly positive and slightly negative charges of polar covalent molecules. So water is one example, and it's the most important example for us because we're biologists and all of our chemistry that we are worried about occurs in water. So we have to worry about the behavior of water a lot. So here, if we look at these three water molecules that I've just circled, the slightly positive hydrogen end of this one is going to face the slightly negative oxygen end of this one, and the same is true over here. And I would bet that if I had a fourth water molecule, its hydrogen would face the oxygen end of this water molecule. So what this means is water likes to stick to itself, and it likes to stick to other things with a partial charge. So that's what gives water its properties. And we'll learn more about that both in future lectures and in lab. All right, so we've been talking about the formation of bonds and exchanging of electrons. All of these things are things that come in the form of chemical reactions. So turning 2 hydrogens and 1 oxygen into water, that's a chemical reaction. So the way that we write these is we write the ingredients, if we're thinking of this as a recipe, the ingredients on the left, and the final product on the right. And we either use a single right arrow, a single left arrow, or this double arrow, which means the reaction can proceed in either direction. So this is the way we write chemical reactions. And in this case, the double arrows, as I said, indicates that the reaction is reversible. So which way the trend is going to depend on the relative amount of reactants and products. So if there are more reactants, the reaction will shift to the right, and if there is more product, the reaction will shift to the left. So the concentration of reactants and products at equilibrium depends on the energy in the chemical system. So let's say that doing this step here requires an input of energy. If there's more energy, you're going to get more product. If there's less energy, you'll get less product. So these concentrations can be altered by the addition of more reactant or product, introducing heat into the system, using chemical catalysts, and these are things like enzymes, and adding other chemical reactants that lead to other products. So there's lots of different ways to set up and change a chemical reaction. This reactant A, reactant B, product C is just a schematic diagram of that. And that is the end of our PowerPoint. So in the next one, we will talk about what happens when molecules get next to each other in ways other than hydrogen bonding, and the behavior of water and a whole bunch of other good stuff. So stay tuned for the next video. Thanks for your attention.